Hello everyone. Let's prove one more theorem on Hilbert space. Here every inner product space is a normed vector space, or we can say linear space. So for proving an inner product space as a normed vector space, we assume Vk be an inner product space. Let u comma v belong to v and a belongs to k. Now we defined the norm. We define norm u as the inner product. U comma u. Okay. So we see that inner product is defined on V. Therefore, norm U is also defined on V. Now, we verify the four properties of a norm function. First property is norm U is greater than or equal to 0. So, as we have already defined, norm U is equal to square root of u comma u, and we know that inner product is always greater than or equal to 0. So norm u is also greater than or equal to 0. Second part, norm u is equal to 0 if and only if u is a 0 vector. So again, norm u is equal to 0 if and only if square root of u comma u is equal to 0 if and only if u is a 0 vector. So the second property is also satisfied. Now we come to third property. Norm of AU is equal to mod A multiplied by norm U. We start from AU squared, and it can be written as, according to this definition, AU comma AU, and again it can be written as inner product of U comma AU, which is again as A multiplied by A conjugate, and it is U comma U, and it is nothing but mod A squared and norm U squared. So now, taking the positive square root, we can write norm of AU is equal to mod A multiplied by norm U. So the third property is also satisfied. Now we come to fourth property. Fourth property is norm of U plus V is less than or equal to norm U plus norm V. Okay, so again we start from here. Norm U plus V squared can be written as U plus V comma U plus V, which is again as U comma U plus V plus V comma U plus V. Distributive property is again applicable. U comma U plus U comma V. Plus inner product of V comma U, and finally inner product of V comma V. Okay, so which can be written as norm U squared plus norm V squared plus inner product of U comma V, plus this can be written as U comma V conjugate. Okay, so now if we assume u comma v as alpha plus iota beta, then obviously u comma v conjugate is alpha minus iota beta. And if we add these two factors, here it is twice of alpha, which can be written as twice of real part of inner product of u comma v. And also we can write alpha is less than or equal to alpha square plus beta square, or this can be written as mod of inner product of u comma v. So here it is less than or equal to norm u squared plus norm v squared, and we can replace this factor by twice of this, because alpha is less than or equal to this much. So initially you can write it as twice of real part of u comma v, and later on we can write it is norm u squared plus norm v squared plus twice of u comma v. Okay, now again we have to use Schwarz inequality, that is less than or equal to norm u multiplied by norm v. Okay, so now we can write norm u plus v whole squared is less than or equal to norm u squared plus norm v squared, and here plus twice of norm u multiplied by norm v. Okay, and again it is norm u plus v squared is less than or equal to norm u square norm u plus norm v whole square, and again taking square root we can write norm of u plus v as less than or equal to norm u plus norm v. So the fourth property is also satisfied. So we can say that V is a normed linear space. Now let's come back to the orthogonality of any two vectors of a Hilbert space. Now we define orthogonality again. We know that if x and y are any two vectors of a Hilbert space, H, then x is perpendicular to y if inner product of x comma y is equal to 0. And also we know that if x is perpendicular to y, then y is also perpendicular to x, inner product of y comma x is also equal to 0. And second property is about zero vector. Zero vector is perpendicular to every vector of h. Or we can say 0 comma x is equal to 0, right? And third property is a scalar multiple of a vector. A is a scalar. If x is perpendicular to y, then ax is also perpendicular to y. We can prove it because x is perpendicular to y implies inner product of x comma y is equal to 0, and also inner product of ax comma y is equal to a multiplied by inner product of x comma y, and from here we can put 0, so it is a0, which is again 0. So inner product of ax comma y is equal to 0. Therefore we can say ax is perpendicular to y. Now we defined a set S perpendicular. Let S be a non-empty subset of H. Then a vector x is said to be perpendicular, or you can say orthogonal, if x is perpendicular to y for all y. So first we have defined the perpendicularity of a vector with a non-empty subset, and now S perpendicular. S perpendicular is the set containing the vectors of H such that inner product of x comma y is equal to 0 for all y. Okay, so this is the perpendicularity of a non-empty subset, and also we can say the two non-empty subsets S1 and S2. If S1 and S2 are any two subsets of H, then S1 is perpendicular to S2 if inner product of x comma y is equal to 0 for all x belongs to S1 and y belongs to S2. Okay, now we prove a theorem on perpendicularity. Here we have a theorem. Let S be a non-empty subset of a Hilbert space H, then S perpendicular is a closed subspace of H. Now we know that S perpendicular is the set containing the elements of H such that inner product of x comma y is equal to 0 for all y. Now we can find 0 comma y is always 0 for all y. Okay, because 0 vector is perpendicular to every vector, so that's why we can say that 0 belongs to S perpendicular, and hence S perpendicular is a non-empty subset. Hence S perpendicular is a non-empty subset of H. Now we assume x1 comma x2 belong to S perpendicular and alpha comma beta are any two scalars. Then as x1 and x2 belong to S perpendicular, therefore x1 comma y is equal to 0 and x2 comma y is also 0 for all y. Now to prove that S perpendicular is a subspace of H, alpha comma x1 plus beta comma x2 comma y can be written as alpha inner product of x1 comma y plus beta inner product of x2 comma y, and these two are 0, so therefore you can say alpha multiplied by 0 plus beta multiplied by 0, and again it is 0. Okay, so therefore this implies alpha x1 plus beta x2 belongs to S perpendicular. Therefore we have proved that x1 comma x2 is perpendicular and alpha comma beta belong to K if it is HK. Then this implies alpha x1 plus beta x2 belongs to S perpendicular. So this is the necessary and sufficient condition for a subspace. So S perpendicular is a subspace of H. Okay, now we have to prove that S perpendicular is a closed subspace of H. To prove that S perpendicular is a closed subspace of H. Okay, and for this we have to show that every limit point of S perpendicular is in S perpendicular itself. Let x be any limit point of S perpendicular. Then we have to show that x belongs to S perpendicular. So here we are assuming that x be any limit point of S perpendicular. Therefore, there exists a sequence xn of points of S perpendicular such that xn tends to x, or we can say limit n tends to infinity, xn is equal to x. Okay, now xn belongs to S perpendicular, then xn comma y is equal to 0 for all y, right? Because xn is the element of S perpendicular, then obviously inner product of xn comma y will be 0 for all y belongs to S. Now this can be written as limit of xn comma y is equal to 0, or it is limit of xn comma y is equal to 0, right? And limit of xn can be replaced by x, so it is x comma y is equal to 0. This implies x is perpendicular to y, and again this implies x belongs to S perpendicular. So the limit point is in S perpendicular, therefore S perpendicular is closed, and hence we have proved that S perpendicular is a closed subspace of H. Okay, that's all for this lecture. See you in the next video.